US Physics Olympiad, year 2018. F equal MA, first round. This year, this Olympiad was split by two exams, A and B, and you can choose to participate either one day for exam A or next week in exam B. And the results was counted separately. That was again 25 problems, and for this amount it was given 75 minutes. Subscribe for this channel to get more problems every day. Problem 1. Which of the following graphs best shows the velocity versus time of an object originally moving upward in the presence of air friction? Solution. First of all, when object is moving, there are two forces acting on it. That's a gravity force, which is constant and is going down, and also air resistance, which depends from speed, and it's always opposite to motion. And it's greater when speed is greater. It means that during all this motion, total acceleration must decrease, and finally it will reach terminal speed, which is negative. On this picture we have case C, in which we have constant acceleration. So it means that looks like there are no air resistance. On other pictures we have terminal speed, but on picture A it's positive. It means that the object always going up, which is not correct. On pictures B and E we have terminal speed equals 0. It means that finally object is not moving, which is not correct. And only on picture D we have terminal speed is negative and acceleration always decreasing. So that's the correct answer. Problem 2. A 3 kilogram mass moving at 30 meters per second to the right collides elastically with a 2 kilogram mass traveling at 20 meters per second to the left. What is the speed of the center of mass of the system after collision? Solution for problem 2. The speed of center of mass is constant, so we can just count it before collision, and we can use formula V speed of center of mass equal this expression, which is 10 meters per second. And this is answer B. Which one is correct? That was a solution for problem number 2. Problem number 3. Ball 1 traveling in the positive x direction strikes an equal mass ball 2 that is originally at rest. All of the following must be true after the collision except. Solution for problem number 3. Let's check all sentences. A. The total final momentum in the x direction equals the initial momentum of ball 1. That's true because we have momentum conservation, and means that this is not correct answer. B. The total kinetic energy after the collision equals the initial kinetic energy of the ball 1. That could be not true because collision could be completely elastic, completely inelastic, or partially elastic. And because this is not completely true, that could be a correct answer. C. The final momentum of the two balls in the y direction adds to 0. That's correct because the initial momentum in direction y is 0. And we have momentum conservation. D. The final speed of the center of mass of the two balls is equal to half the initial speed of ball 1. That's true because final speed of center of mass it's not changing during collision, and it must be same as before collision, and it was equal half of the speed of the first ball. This is true, and this is not correct answer. E. The balls can't both be at rest after the collision. That's true because a center of mass is moving, and both or one of them must move. So that's correct, and means that this is not correct answer. And we have correct answer is B. Problem number 4. A satellite is following an elliptical orbit around the Earth. Its engines are capable of providing a one-time impulse of a fixed magnitude. In order to maximize the energy of the satellite, the impulse should be. Solution for problem number 4. We can write equation for change of kinetic energy for fixed impulse. Fixed magnitude of impulse, it means that dV must be fixed. So it means that the change of kinetic energy for this impulse equal this expression, where V multiplied by delta V, that's a dot product. So, and this function has a maximum when V has a maximum, and delta V is parallel to V in the same direction. And we know that maximum kinetic energy we have when satellite going through perigee. So that's the answer for problem 4. Answer is A. Directed along the satellite's velocity and applied when satellite is in its perigee. That was solution for problem number 4. Problem number 5. Two masses are attached with the pulleys by a massless rope on an inclined plane as shown. All surfaces are frictionless. If the masses are released from rest, then the inclined plane. Solution for problem number 5. Here we can see that tensions from mass m1 and mass 2 are vertical. It means that they are not creating any horizontal force on this incline. It means that this incline will stay and they will not move. And the correct answer is E, does not move. That was a solution for problem number 5. Problem number 6. A packing crate with mass m equal 115 kg is a slide up a 5 meters long ramp, which makes an angle of 20 degrees with respect to the horizontal by an applied force of 1000 newtons directed parallel to the ramp's incline. A frictional force of magnitude 400 newtons resists the motion. If the crate starts from rest, what is its speed at the top of the ramp? Solution for problem number 6. Here we can use work energy theorem, and we see that applied force F minus force of friction F small multiplied by distance 5 meters, that must be equal to total potential energy in the end of this incline plus kinetic energy, which will give us an equation like this. From here we can find immediately what is speed V. That will be this expression, and after putting numbers we will get 4.24 meters per second, which is answer A. That was a solution for problem number 6. Problem number 7. A car has a maximum acceleration of a0 and a minimum acceleration of negative a0. The shortest possible time for the car to begin at rest, then arrive at rest at a point a distance d away is next one. Solution for problem number 7. The best strategy for this trip is to move half of this distance with the maximum acceleration, reach this half distance, and after that move with the maximum deceleration to get in the rest in the end of the strip. So it means that we can count what is total time. Total time to cover half of this distance is this square root from d over a0. And the same time we will spend with the deceleration negative a0. So it means that correct answer is 2 times of this t, which is E, correct answer. That was solution for problem number 7. Problem number 8. A disk of radius r small rolls uniformly without slipping around the inside of the fixed hoop of radius big R. If the period of the disk's motion around the hoop is t, what is the instantaneous speed of the point on the disk opposite to the point of contact? Solution for problem number 8. First, we can find what is the speed of center of this small disk. This speed equal to distance covered by this center, which is 2 pi multiplied by big R minus small r and divided by period t. And now, because this speed is constant, Vc, and the instantaneous speed of this top of this small disk is just proportional to distance from the point of contact. It means that this distance twice greater than distance to the center of this disk. It means that speed of this point will be twice greater than Vc, which is this one. And this is the answer D. That was solution for problem number 8. Problem number 9. A uniform stick of mass m is originally on a horizontal surface. One end is attached to a vertical rope, which pulls up with a constant tension force F, so that the center of the mass of the stick moves upward with acceleration a less than g. The normal force N of the ground on the other end of the stick shortly after the right end of the stick leaves the surface satisfies next conditions. Solution for problem number 9. Here we can write two equations. One equation net force in vertical direction, and other equation is rotational motion. There are no equation for horizontal motion. So first of all, let's write a vertical equation. We have MA equal normal force plus force F and minus gravity force. That's a vertical equation. Rotational motion. We have two forces which create torques around the bottom left corner of this stick. It is force F, for which we have torque equal FL, where L is the length of this stick, and minus torque created by gravity force, which is mg multiplied by L over 2. And that must be equal I alpha, where I is moment of inertia and alpha is angular acceleration. Now let's write what is the relation between alpha and A. Obviously alpha equal 2A over L, and also moment of inertia for this stick equal to 1/3 ml square. Now we can put these expressions to the second equation for rotation, and we will get expression for force F using acceleration A and acceleration of free fall. And now we can exclude this F from the first equation, put it here, and find that normal force equal 1/3 MA plus 1/2 mg. And now, because we know inequalities for acceleration a that's greater than 0 but less than g, we finally can find what are the limits for normal force. That will be between 1/2 mg and 5/6 mg. If we check answers, we can see that only B can satisfy these limits. So B is the answer for problem 9. Problem number 10. Which of the following graphs best shows the acceleration versus time of an object originally moving upward in the presence of air friction? Solution for problem number 10. Initially, when object moving upward, there are two forces acting on it. That's a force of gravity and also force of air friction, which is going the same negative direction. It means that the original acceleration must be less than g, which is less than negative 10. And finally, when object reach the terminal speed, acceleration must approach 0. On this graph, we see that only on graph E we have such behavior for acceleration. In other cases, we don't see any terminal speed behavior. And also on graph E, we have initial acceleration is less than negative 0, and it's constantly increasing, which is correct. So the correct answer is E. Problem number 11. A light uniform ideal spring is fixed at one end. If a mass is attached to the other end, the system oscillates with the angular frequency omega. Now suppose the spring is fixed at the other end, then cut in half. The mass is attached between the two half springs. The new angular frequency of oscillations is next one. Solution for problem number 11. Let's write the equation for the first case. We can write that force F equal negative kx, where x is displacement, and this force equal ma, and this is the regular equation for harmonic oscillation with the angular frequency omega equal square root from k over m. In the second case, we have two springs, each half of initial spring. It means it has now constant k, which is a double compared to the first string. Have equation F1 equal negative 2kx, where F1 is the force for each spring. And now they act both on this mass, so the force must be doubled. It means that equation will be ma equal negative 4kx and omega 1 equal 2 omega. That's the answer D, which is a solution for problem number 11. Problem number 12. A group of students wish to measure the acceleration of gravity with a simple pendulum. They take one length measurement of the pendulum to be L equal 1 meters plus minus 0.0 meters. They then measure the period of a single swing to be t equal 2.00 plus minus 0.10 seconds. Assume that all uncertainties are Gaussian. The computed acceleration of gravity from this experiment, illustrating the range of possible values, should be recorded as following. Solution for problem number 12. First, let's write equation for period of simple mathematical pendulum. This is the formula. From here we can find what is acceleration of free fall. So we have a G equal 4 pi square multiplied by length L over period square. We can use this formula to find what is the measurement for acceleration and uncertainty. If measurement for length and period are independent, we can use a regular formula to find what is the uncertainty for G. We can use a mean quadratic formula for that. Here dg over dl, that's a partial derivative. It means that we can take a derivative from this expression in other variable as a constant. So it means that delta g over delta l equal this expression, or g over l, and delta g over delta t equal this expression, or negative 2 multiplied by g over t. Now we can put this expression in this formula and find that delta g over g squared equal this expression, and finally we have g equal 9.87 and delta g equal 1.1. So it means that we should not count the second digit after the point, and we can round this by 9.9, and the final result is this one: g equal 9.9 plus minus 1.1 meters per second square, which is answer D. That was a solution for problem number 12. Problem number 13. A massless cable of diameter 2.54 centimeters, which is 1 inch, is tied horizontally between two trees 18 meters apart. A tightrope walker stands at the center of the cable, giving it a tension of 7,300 newtons. The cable stretches and makes an angle of 1.5 degrees with the horizontal. The Young's modulus is defined as the ratio of stress to strain, where stress is the force applied per unit area and the strain is the fractional change in length dl over l. The cable's Young's modulus is next one. Solution for problem number 13. First, let's count what is stress here. Stress equal force divided by cross-sectional area, which is pi r square, and after when we put numbers we will get this result: 14.4 multiplied by 10 power 6 newtons per square meter. Next one, we have to find what is strain. Strain we can find from simple geometry, so we have dl over l equal 1 minus cosine theta over cosine theta. For small angles that will be approximately this expression or this expression. And after putting numbers we have this number. And the last step to find what is Young's modulus, which is stress over strain. After putting numbers we will get 4.2 by 10 power 10 newton per square meter, which is answer E. That was a solution for problem number 13. Problem number 14. Three identical masses are connected with the identical rigid rods and pivoted at point A. If the lowest mass receives a small horizontal push to the left, it oscillates with period T1. If it instead receives a small push into the page, it oscillates with the period T2. the ratio T1 over T2 is next one. Solution for problem number 14. In both cases we can write expression for period using a formula for physical pendulum. This formula is 2 pi multiplied by square root from I over mgx, where I is moment of inertia, big M, that's total mass, and x is distance from point of rotation A to the point of center of mass, x. In the first case we have I equal 3ml square, big M equal 3m, and x equal L over 3, and total period equal 2 pi multiplied by square root from 3L over G. In the second case, only lowest mass participating in this oscillation. These two other masses, they are not moving. So it means that I equal ml square, mass equal small mass, and x equal L. In that case, period equal 2 pi multiplied by square root from L over G. And T1 over T2 will be square root from 3, which is answer C. That was solution for problem number 14. Problem number 15. A satellite is in a circular orbit about the Earth. Over a long period of time, the effects of air resistance decrease the satellite's total energy by 1 joule. The kinetic energy of the satellite. Solution for problem number 15. We have total energy equal kinetic energy plus potential energy. For circular orbit in any point, we have potential energy equal negative 2k, where k is kinetic energy. It means that total energy equal negative k. It means that if we decrease total energy by 1 joule, kinetic energy will increase by 1 joule, which is answer A. That was solution for problem number 15. Problem number 16. A cylindrical space station produces artificial gravity by rotating with the angular frequency omega. Consider working in the reference frame rotating with the space station. In this frame, an astronaut is initially at rest, standing on the floor, facing in the direction that the space station is rotating. The astronaut jumps up vertically relative to the floor of the space station, with an initial speed less than that of the speed of the floor. Just after leaving the floor, the motion of the astronaut relative to the space station floor is next one. Solution for problem number 16. Let's do this problem with a free space frame of reference. In this frame of reference we have initial position for astronaut in the bottom of this red line, and the space station rotates clockwise. If vertical speed of astronaut is less than horizontal speed to the left, we have this red line of this trajectory of astronaut will be with the angle less than 45 degrees, and he will land below the center of this space station, at some point on the surface of this station. And because total speed of this astronaut greater than speed of any point of the floor, and he is moving by straight line to the final point, he will reach this point earlier than point of floor from which he was jumped. And from other hand, we can check what is the projection of his velocity on a radial direction in any point, and this projection will always decrease. So it means that astronaut always has a part of acceleration going from the center of this space station. From all these sentences, only sentences B is a correct one. Always has a component of acceleration directed toward the floor. That's true. And they land in the front of the point they jumped from, which is always true. So B is correct answer, and this is the solution for problem number 16. Problem number 17. A stream of sand is dropped out of a helicopter, initially moving at a constant speed v to the right. The helicopter suddenly turns and begins moving at constant speed v to the left. Neglecting air resistance on the sand, what is the shape of the stream of sand as viewed from the ground? The black dot represents the helicopter. Solution for problem number 17. If sand is dropped out of a helicopter with a constant velocity, it always remains directly beneath the helicopter. Thus, the path of the sand should be two straight vertical lines. That's answer D. And this is a correct solution for problem number 17. Problem number 18. A mass M is attached to a thin rod of length L so that it can freely spin in a vertical circle with a period T. The difference in the tensions in the rod when the mass is at the top and the bottom of the circle is next one. Solution for problem number 18. First of all, let's write expressions for tensions in highest and lowest position. Due to circular motion in highest position, we have mv1 square over L equal tension T1 plus mg, because both forces directed down. In lowest position, we have mv square over L equal T2 minus mg, because now tension going up and gravity force going down. That was from circular motion. Next equation is for energy conservation. In the highest position, we have kinetic energy mv1 square over 2 plus potential energy compared to the lowest position, which is 2mgl. That must be equal to kinetic energy in lowest position, which is mv2 square over 2. If we subtract from second equation first equation, we can find what is the tension difference. T2 in lowest position minus T1 in the highest position. And from energy conservation, we can find that this difference equal 4mgl. And now using these two equations, we can find that T2 minus T1 equal 6mg, which is answer C, and this is a correct solution for problem number 18. Problem number 19. Raindrops with the number density of n drops per cubic meter and radius r0 hit the ground with a speed v0. The resulting pressure on the ground from the rain is p0. The number density is doubled, the drop radius is halved, and the speed is halved. The new pressure will be next one. Solution for problem number 19. Each drop has 1/8 the mass and 1/2 speed. So it means that momentum is 1/16. The rate at which they hit the ground is the same, since the number density is doubled, but the speed is halved. Thus, the pressure is P0/16. That's answer E, and this is correct answer for problem number 19. Problem number 20. A spring stretched to double its unstretched length has a potential energy U0. If the spring is cut in half and each half spring is stretched to double its unstretched length, then the total potential energy stored in the two half springs will be next one. Solution for problem number 20. First, let's write expression for potential energy of a stretched spring. That will be 1/2 kx squared. For two springs, we have potential energy equal 2 times 1/2 multiplied by new spring constant 2k and multiplied by stretch, which is x over 2 squared, which finally will give us the same potential energy, U0. From other hand, we have that we stretch two halves, and it doesn't matter if we cut this spring or not cut, because if we connect them together, we will stretch them as in initial experiment. So it must be the same potential energy. That's answer C, and this is a correct answer for problem number 20. Problem number 21. A ping pong ball, a hollow spherical shell with mass m, is placed on the ground with the initial velocity v0 and 0 angular velocity at time t equals 0. The coefficient of friction between the ping pong ball and the ground is mu s equal mu k equal mu. The time the ping pong ball begins to roll without slipping is next one. Solution for problem number 21. First, let's write the equation for translational and rotational motion. Because this ping pong ball is moving to the right with the initial speed, it will contact with the surface with the friction. It will decelerate with acceleration a. We can find from equation ma equal minus mu mg, where mu mg is a force of friction. And also we have rotational motion. For rotational motion we have I alpha equal mu mgr, where I is moment of inertia, alpha is angular acceleration, mu mg, that's force of friction, and r is the distance from point of contact to the center of mass around which this ball is rotating. From here we can find that acceleration equal negative mu g, and because for hollow sphere we have moment of inertia equal 2 over 3 mr square. From second equation we can find what is angular acceleration. That will be 3 over 2 mu g over r. Now let's write equation for velocity and for angular velocity. For velocity we have this equation, velocity equal v0 plus at, and angular velocity equal alpha t, which is this one. Also, in time when this ball moving without slipping, we have v equal omega r. And now, using all these expressions, we can make equation 3 over 2 mu gt equal v0 minus mu gt. And from here we can find what is total time when ball begins to roll without slipping. That will be 2 over 5 v0 over mu g, which is answer A, and this is the solution for problem number 21. Problem number 22. A small hole is punched into the bottom of a rectangular boat, allowing water to enter the boat. As the boat sinks into the water, which of the following graphs best shows how the rate water flows through the hole varies with time? Assume that the boat remains horizontal as it sinks. Solution for problem number 22. By Archimedes' principle, the difference in the outer and inner water levels always remains the same. Then the amount of pressure forcing the water through the hole remains the same by Bernoulli's principle. So the rate of sinking is constant. That was answer A, and that was a solution for problem number 22. Problem number 23. The coefficients of static and kinetic friction between a ball and a ramp are mu s equal mu k equal mu. The ball is released from rest at the top of the ramp. Which of the following graphs best shows the rotational acceleration of the ball about its center of mass as a function of the angle of the ramp? Solution for problem number 23. This problem could be solved using excluding method. We can check that for zero angle, acceleration must be 0 because ball is stationary. It means that choice A is impossible and choice E is impossible. Also for 90 degrees, that must be 0 because there are no friction. It means that choice B impossible and choice D impossible. So we have only choice C left. And we see that here we have increasing angular acceleration with the angle increasing till some critical angle, and after it's decreasing to 0. So that's the solution for problem number 23. But also we can count it by formulas. For small angles we have no slipping. It means that linear acceleration proportional to angular acceleration and equal alpha r. We have a linear equation and angular equation describing linear and angular acceleration with using a force of friction. And from here, if we use a formula for moment of inertia, which in common case equal beta mr square, we have angular acceleration equal this expression. Here we can see that this angular acceleration increasing from 0 till some kind of a critical angle where we start to slip. And we can find this critical angle using a limit for force of friction. From one hand we can find that force of friction equal beta mr alpha, and from other hand we can put here maximum possible friction. That will be this expression. And from here we can find what is the critical angle. That will be this expression, 1 plus beta over beta multiplied by mu. When we increase theta more, we have motion with a slipping, and now we have to write different equations. Here we just use equation for rotational motion, and using formula I equal beta mr square, we can find that angular acceleration equal this expression. So we can use this expression for tangent theta more than this expression. And finally we have a solution for two cases. For both cases, small angles less than tangent theta less than this expression. We have alpha is increasing function, and for tangent theta more than this expression we have a decreasing function. These both functions, they are concave down, and also they have a sharp angle. So that's the definitely graph C. And this is the answer for problem number 23. Problem number 24. A mass is attached to one end of a rigid rod, while the other end of the rod is attached to a fixed horizontal axle. Initially the mass hangs at the end of the rod and the rod is vertical. The mass is given an initial kinetic energy K. If K is very small, the mass behaves like a pendulum, performing small angle oscillations with a period t0. As k is increased, the period of the motion for the mass. Solution for problem number 24. First of all, let's write the equation for angular motion of this mass. We have equation that angular acceleration equal negative g over L multiplied by sine theta. For small theta, sine theta almost equal theta, and in this case we have a period equal t0. But when theta is increasing, this function increasing not linearly but slower. It means that restoring force increasing slower, and it means that period will increase. And when amplitude increasing till pi, this period will increase till infinity, but after this angle reach pi and will go further, periodic motion turning to rotational motion. And now when we increase k, this period of rotational motion will decrease and going to 0 when k is going to infinity. That's the answer for problem number 24, and this is E, correct answer. Initially increases and then decreases. Problem number 25. Alice and Bob are working on a lab report. Alice measures the period of a pendulum to be 1.013 plus minus 0.008 seconds, while Bob independently measured the period to be 0.997 plus minus 0.016 seconds. Alice and Bob can combine their measurements in several ways. First way, keep Alice's result and ignore Bob's result. Second way, average Alice and Bob's results. Third way, perform a weighted average of Alice's and Bob's results with Alice's results weighted 4 times more than Bob's result. How are the uncertainties of these results related? Solution for problem number 25. Let's Alice's measurement have uncertainty dx, so Bob's has uncertainty 2dx. The uncertainty obeys the following rules, which can be derived by identifying the uncertainty with the standard deviation. A. Scaling. If x has uncertainty dx, then cx has uncertainty c dx. B. Addition in quadrature. If x has uncertainty dx and an independent measurement y has uncertainty dy, then x plus y has uncertainty square root from squares of dx and dy. Then the uncertainties of the 3 possibilities are: first method, dx; second method, this one, square root from dx squared plus 2 times dx squared over 2. This is uncertainty for x plus y divided by 2. That will be square root from 5 over 2 dx. And the third one is weighted, which is a square root from 4 times dx squared plus 2 times dx squared, which is 2 over square root 5 dx. Definitely highest uncertainty is second one, lowest uncertainty is third one, and first one in the middle. So it means that answer will be B. Method 3 has the lowest uncertainty and the method 2 has the highest uncertainty. It's the solution for problem number 25.